In this section, we are ready to implement the solution. So in this one, we are going to do the detailed steps of the solution, detailed calculations, doing the algebra right, and making sure the parameters are chosen properly. So we have decided to use Heisler chart as the way to get solution. So note, to read Heisler chart, you first have to decide which set of lines. The set of lines correspond to different values of m, and m depends on the boundary conditions. M depends on the ratio between external and internal resistance. M, if you look at it, is really just inverse of Biot number. Okay. Then once you choose the set of lines, within the set of lines there are a number of lines, and we need to choose the one corresponding to our position. So after we choose based on boundary condition, then we need to choose which position, and position is x, and the n value that you see here, it corresponds to different values of x. It's a non-dimensional position. So once we have chosen n, then we have a single line, and our y-axis is the non-dimensional concentration. In this case, we are given a moisture for which we have to find the time. So we're given the y value for which we have to find the x value. As we start to compute m, note m is given by these quantities. Diffusivity is given, and it is diffusivity of moisture in the air in the compost, not moisture through the solid, but through the air space in the compost. Then we have K star that is given, and then HM is the mass transfer coefficient. You note that the unit for mass transfer coefficient is quite different from unit of heat transfer coefficient, although it is quite analogous. Now finally we have to choose the L, the length. Now note that when we did the problem in class, it corresponded to a boundary condition of drying air, not on one side, but on both sides. But here, the drying air is only on one side, and the bottom is impermeable. Note that the problem that we did in class, which is drying air for both sides of a pile, for that the center line here is impermeable. So this impermeable layer really corresponds to having a slab twice the size, but dried symmetrically from both sides. In that case, the center boundary would be same as the bottom boundary now. So these two problems are equivalent. And because we did this one, and for which 2L was 0.6, then the L we need is 0.3. So that's how we get the L equals 0.3. Now we get into computing N. N corresponds to the position variable. Which position are we interested in? Now notice it says that the most moist position. If you're drying from this surface, and it's also not losing moisture from any of the other three surfaces, then at any time this will be your most moist position. Since we are calculating x from this location, then x over L is going to be 0. We are now in a position to find the y value, which is m minus m infinity over mi minus m infinity, m standing the same as concentration. So m is moisture. So m, in this case, m is the final moisture at the point we are interested in. So this is given to be 0.3. Mi is the initial moisture. So initial moisture is given to be 1. Now let's look at m infinity. What is m infinity? Now you may think, or we may think, that m infinity is just moisture in the air. But we have to be careful. The problem we are solving is in the slab. It's inside the slab. It's in the solid. So we cannot use moisture in the air in the expressions that really only relate to the solid. But notice that this m infinity really is whatever moisture would correspond to the condition of air far away from the surface. So we're given the moisture in the air to be 20% relative humidity. We're also given the moisture isotherm for this compost material. So you can see the curve here. What this curve says is at 20%, if you have compost that is in contact with 20% relative humidity, it's going to have 0.03 kilograms of water per kilogram of solid. In other words, this much moisture in the compost is in equilibrium with this much relative humidity or moisture in the air. Since this is the condition given to us, then corresponding to that, the equilibrium moisture content is 0.03, and that's what is my m infinity. So this is moisture in the solid that corresponds to or in equilibrium with the 20% relative humidity air. So if I plug all this in, then I get the y value 0.278. So y value is somewhere here, 0.278. Now we need to read, except that the m value that we got, there are no lines, no set of lines correspond to m equals 0.15. So what we would do is interpolate between m equals 0 and m equals 0.5, m equals 0 and n equals 0, this point, and m equals 0.5 and n equals 0. So between these two, we interpolate it, and by interpolating, we get the x value here to be 0.8. And that x value is the non-dimensional time, Fourier time. So time t is equal to f sub o L square over DAB. So we put in all the values to get the final time t equal to 20 hours, which means this moisture 0.3 would be reached at the center, at the bottom of the compost pile in 20 hours. For this last part of the problem, we would like to find what is the moisture at the top surface for the time that we have calculated in the previous slide, and for which the non-dimensional time is 0.8. So at 0.8, we simply have to choose the right line, and for which we just need to read the y value. But notice we have again the same problem, that m value, which depends on the boundary condition. So it is the same as before. So we have m equals 0.15, for which we have no line. So again, we have to interpolate. So we have a little bit of a problem. So for m equal to 0, and now n is 1 because it is the top surface. So x is L. So m equals 0, n equals 1, we cannot read the chart. But we do know that if m is 0, which really means h goes to infinity, then the surface m would be at m infinity, which means this the y-axis is going to be 0. And for m equals 0.5 and n equals 1, so that's this curve or this line, we can read that one, and that's 0.21. So this is my 0.21. And then, so we have 0 for m equals 0 and 0.21 for m equals 0.5. So for 0.15, we interpolate in between and get the y-axis. From there, we can actually get the details of the m, and then m comes out to be 0.0911 kilogram water per kilogram dry solid. So this is the moisture at the surface after so much of drying. The time for which the non-dimensional time is 0.8.